So again, Assalamualaikum and good evening. So we will start with our session for today. Hopefully we'll be able to finish up everything on the three-phase inverter, particularly on the all the example that being included in the lecture notes. So I will share the screen. So if let's say that you have any question, just open up your mic and ask the question. Because I'm using only one device at the moment, so I can't see if let's say that you put the question in the chat box. Okay, so did we stop at this slide, which is three-phase inverter with 120? Dia stop sampai mana? Is it this one, this slide ke? Is it other slide? Did we discuss on this exercise too?
Yes.
Yes, okay. So, ini slide ni kita dah tengok belum? Have a look.
Belum.
Alright, so we'll start from this onwards. Right, so we'll first kita akan pergi on the second control mode for three-phase inverter, which is what we call as 120 degree conduction. Previously, we have three-phase with 180. So first thing about this, whether it's 180 or 120, the first thing that you need to make sure that you are familiar with is this one here, the gating signal waveform. This is for 180. So you can see for 180, there are three switches that will be turned on at every 60 degree interval. If let's say you look vertically, okay, so there are three switches that are being turned on for every 60 degree. Okay, so each of these 60 degree intervals will be presented by a mode, which is from mode 1 until mode 6. Okay, next, this is all the analysis from mode 1 until mode 6. So later on you can refer to this. So we already cover from mode 1 until mode 6 for 180 conduction. So now we proceed with 120 conduction, which is it's simpler as compared to 180. So for 120 conduction, okay, the first statement is that each switch conduct for a period of 120. So from S1 until to S6, every switch will conduct for a period of 120 in one cycle. So from 0 to 2 pi, okay, so every switch will conduct for a period of 120. So for 120 conduction, there are two switches that will be turned on at every 60 degree interval. How to see these two switches, which switch they are turned on and off for every 60 degree interval? We can look that at our gating signal waveform. Okay, where we go to this one here. Yeah? Okay, this is the gating signal waveform for 120. Okay, we will start with S1. So S1 will turn on for a period of 120. So which is it will start to turn on from 0 and it will maintain on until complete conduction of 120. Then it will be off. Which is in this case it will off at 120. Okay, 60 degree delay from S1. S2 will start to conduct, which is from 60 degree, and it will continue to conduct until complete 120. So it will stop at or off at 180 degree. 60 degree delay from S2, S3 will start to conduct, which is at 120. Okay, and then it maintains to turn on. Conduct is turned on, right? Until complete 120 degree. Once it's completed, then it will be off, which is at 240 degree here. Right. And then S4, 60 degree delay from S3, S4 will start to conduct, which is at 180, and then it will maintain conduction until complete 120, so it will off at 300 degree. Same goes with S5, it will turn on at 240 degree until complete conduction, which is it will be off at 360. S6, it will conduct at 300 and then it will continue to conduct until 360. However, this switch is only managed to turn on for 60-degree period. So it needs another 60-degree to complete the conduction. So it will work. So this S6 will be returned back to the reference, which is at 0, to continue the conduction to fulfill 120. So that's why you can see S6 will be turned on from 0 to 60-degree. Okay, and then from this getting signal waveform, if let's say you look vertically, okay, in order to determine the switches for each of the modes, so you can we can summarize here, which is for mode A, mode 1, the duration is from 0 to 60. There are two switches that will be turned on, S1 and 6 for mode number 1. Okay, and then for mode number 2, the period is from 60 to 120. S1 and S2 will be turned on. For mode number 3, vertical, look vertically, you can see S2 and S3 are turned on. The rest will be off. Mode number 4, it will be S3 and S4 here. Mode number 5 is S4 and S5. Mode number 6, S5 and S6. So basically, this is how we extract the information from our gating signal waveform here. Right. That's what we need to do, is that we need to do some analysis to find the level for the line-to-line voltage and phase voltage for inverter using 120-degree conduction. Okay, how to do that? There are before that, the connection, all the upper switches will be connected to the positive terminal of your DC link voltage, which is the odd number, S1, S3, S5. All bottom switches, which is the even number, will be connected to the negative terminal of your DC link voltage. So we'll start with mode number 1. Mode number 1, we have S1 and S6. S1 is the upper switch for phase A. S6 is the bottom switch for phase B. So since there are only two switches that being turned on in each of the phases for 120, so you can predict that there will be only two resistor, two load. Okay, so the connection will be, this resistor will be connected in series. So you have your DC link voltage. Okay, the upper switch, remember, will be connected to the positive link of your DC. So in this case, is S1, right? S1 is the switch that in phase A. So the load will be RA. Okay, and then bottom switch, this is S6 is the bottom switch, even number, will be connected to the negative terminal here of your DC link voltage. So which is, it will be represented by RB. And RC, it will be open circuit since there are no switches that being turned on for this particular mode. Okay, so there are 4 steps similar to inverter with 180. Number 1, find the equivalent resistor. R equivalent will be equals, in this mode number 1, RA plus with RB. Okay, RA plus with RB. Okay, so if let's say that you have a balanced load where the value of RA is the same as RB, is the same as RC, you can represent this resistor RA, RB, and RC with a single R like this. So we substitute RA and RB with R and R. So you get R plus R, you get 2R. Okay, next. Step number 2, you need to find the current. Current, we are using Ohm's law. I will be equal to VDC over R equivalent. So from A, R equivalent is equals to R, right? So VDC over 2R. Okay, this is for balanced load. If let's say that you have unbalanced load, okay, you can't represent VDC over 2R here. So you need to, this is the one, VDC over RA plus RB, which is this one over here. All right. Okay, and then in part C, okay, part C, you need to find the phase voltage. Okay, VAN, VBN, and VCN. Okay, VAN, look at here. This is voltage across your RA. will be equals to I multiplied by RA. Okay, I in step 2, which is VDC over 2R. So we substitute I with VDC over 2R multiplied by RA. We represent by a single R like this. So R, these 2R can be cancelled. So the answer will be equals to VDC over 2 for VAN. Okay, VBN, you look at here. So it has a reverse polarity between the voltage and current here. You can see the current is flowing this way. Meanwhile, the voltage is flowing across opposite direction. So you have to add this negative sign over here. VBN will be equals to negative I multiplied with RB. Okay, I in step 2, substitute in this equation of VBN, you will get negative VDC over 2. So VCN will be equals to 0 since there are no switch that being turned on for for mode 1. Yes. Step number 4, you need to find your line-to-line voltage, VAB, VBC, and VCA. So VAB will be equals to VAN minus VBN. So you VAN you can take from this step number 3, VDC over 2, minus VBN is negative VDC over 2. So negative become positive. So you get positive VDC. That is for your VAB. Okay, VBC is it will be VN minus VCN. VBN from step number 3 is negative VDC over 2. Substitute in here. Minus VCN. Our VCN is 0 kan, kosong. So you get negative VDC over 2. Okay, you punya VCA is VCN minus VAN. Our VCN in step number 3 is 0. Minus VAN is VDC over 2. Okay, so 0 minus VDC over 2, you get negative VDC over 2. So these are the the analysis that need to be done in each of the mode. 4 step. Number 1, you need to find the equivalent resistor. There's one here. Step number 2, find the current. Step number 3, find the phase voltage. Step number 4, find the line-to-line voltage. If, let's say, you need to find a phase current, okay, you can use this formula over here. IA will be equals to VAN divided by RA for your phase current, IA. IB VBN divided by RB, phase current B, and IC VCN divided by RC for phase current C. Okay. So next, so once you have done all this, you can move to the next mode. So for mode number 2, the switch that been turned on, you can refer back to here, which is S1 and S2. Okay, S1 is the upper switch for phase A, S2 is the bottom switch for phase C. Again, if let's say that you don't recall the numbering, in order to figure out which switch are connected to which. Okay, you can always write this, yeah? S1, S3, S5, S4, S6, S2. So write it down so that you are aware on the numbering for the switches. So S1 and S4, again, the load will be connected is RA. S3 and S6 is RB. S5 and R2 is RC. Okay. Right. So we next we draw the equivalent circuits where we have the input voltage is VDC. Since S1 is the upper switch for phase A, so it will be connected to the positive terminal of your DC line voltage. Okay, S2 is the bottom switch for phase C. It will be connected to the negative terminal of your DC line voltage. So for mode number 2, there are no switches that been turned on for phase B. So basically your phase B is 0. So VBN will be equals to 0. Okay, again the same step. Step number 1, you need to find the equivalent resistor. In this case, it will be RA plus with RC. So if let's say that you have a balanced load, you can represent RA and RC with a single R like this. You get 2R. Okay, and then step number 2, find the current. Okay, the current will be equals to VC over 2R. This is for balanced load. If let's say that you have unbalanced load, you need to use this equation over here. Basically, it's the same. It's just that in terms of different representation. This is balanced load. Okay, this is for unbalanced load. Okay, right. Next, we need to find in step number 3, find the phase voltage. VAN, we will get VDC over 2. VBN is 0, and your VCN, you will get negative VDC over 2. Okay, as for line-to-line voltage, VAB also VDC over 2, VBC is also VDC over 2, and VCA is negative VDC. So make sure you be able to substitute all the value in step 3 inside here, so that you'll be able to have this answer for the line-to-line voltage. Okay, next. Okay, sorry. Okay, we go for mode number 3. Okay, for mode number 3, we have S2 and S3. Again, if let's say that you are not sure, always refer to this getting signal waveform. Okay, and then you write down this. Mode number 3, we have S2 and S3, right? S2 and S3 here. Okay, so S2 is the bottom switch for phase C, S3 is the upper switch for phase B. Remember, 3 is the odd number upper, 2 is the even number bottom. Okay, so the upper switch, in this case, S3 is the one that being connected to load RB. So RB will be placed at positive terminal of your DC link voltage, and RC will be placed at negative terminal of your DC link voltage. Okay, and then your equivalent resistor REQ, it will be equals to RB plus with RC. Okay, for balanced load, it will be equals to 2R over here. So the current, again, we are using Ohm's law. Current will be equals to VDC over 2R for balanced load. For unbalanced load, you can directly use this equation, which is I will be equals to VDC divided by RB plus RC. Okay, phase voltage VAN will be equals to 0 since there are no switch that be turned on for phase A. VBN, VDC over 2, and your VCN will be equals to negative VDC over 2. And this is for the line-to-line voltage. VAB will be equals to negative VDC over 2. VBC is positive VDC. And VCA is negative VDC over 2. So make sure you know, just follow the step, and then you can in each of these modes over here, so that you'll be able to substitute the value. If let's say that once the value that been given in the question, you can substitute the value directly to find the required value for the phase voltage and your line-to-line voltage. Okay. Okay, next we go for mode number 4. Okay, for mode number 4, we have S3 and S4. Okay, S3 is the upper switch for phase B, S4 is the bottom switch for phase A. Okay, remember for bottom switch, always connect to the negative terminal. Okay, upper switch connect to the positive terminal of your DC link voltage. Okay, so you get this equivalent circuit like this. So step number 1, R equivalent will be equals to RB plus with RA. Okay, step number 2, the current will be equals to VDC over R equivalent, whether it's 2R or RB plus RA. So you can have this either one. So it depends on the load. If let's say that balanced load, again, this one here. If unbalanced, you use this equation here. So VAN will be equals to is VDC over 2 here is negative VDC over 2. Okay, VAN will be equals to negative VDC over 2. This one here for balanced load. If I say that it's unbalanced load, you use this equation here. Okay, VAB will be equals to VDC over 2 and VCN will be equals to 0. And this is the level for your line to line voltage. VAB will be equals to negative VDC. VBC, VDC over 2, and VCA is also VDC over 2. Okay, so this is for mode number 5, which is we have S4 and S5. S4 is the bottom switch for phase A. S5 is the upper switch for phase C. So equivalent resistance will be RC plus with RA or 2R. Okay, this is the value for the current, equation for the current, and these are the phase voltages and your line to line voltage. Okay, so this is for mode number 5. Okay, so make sure you follow this working step so that you don't miss the step in order to get this value for your phase voltage and your line to line voltage. Okay, so as for next, this will be your mode number 6. Okay, mode number 6, you will have switch S5 and S6. Okay, you can always refer back to the gating signal waveform to check on this here. Okay, S5 is the upper switch for phase C, S6 is the bottom switch for phase B. Okay, step number 1, you need to find the equivalent resistor. In this case, it will be RC plus with RB, or let's say you have a balanced load, it will be equals to 2R. Okay, step number 2, you need to find your current. So it will be VDC over R equivalent. Okay. VDC over 2R. Okay, step number 3, you need to find the phase voltage, VAN. There are no switch that been turned on for phase A, so it will be equals to 0. VBN, negative I multiplied by RB. Okay, VCN, it will be VDC over 2. So this is for your VCN. Okay, your line to line voltage VAB, VAN minus VBN. It will be VDC over 2. VBC is negative VDC, right? Negative VDC over 2 minus VDC over 2. Okay, so you get negative VDC. So VCA okay, we get VDC over 2. So these are the level for your phase voltage and your line to line voltage. Okay. Right, so basically we have a complete analysis covering mode 1 to mode 6 for the inverter with 180-degree conduction. Okay, so next, here, so this is the waveform of 100 inverter with 120. So the first one, as I think you're already familiar with this gating in a waveform. Okay, I have shown this. We already construct this gating in a waveform during the lab session, and also we proved that the theoretical waveform of your phase voltage and your line to line voltage using 180 and 120, they are the same, which is they are correct according to the theoretical. Okay. So this is the phase voltage. As you can see, the shape are square. Okay, it has three level of output, which is this is VDC over 2, VS over 2 is VDC over 2, this is 0, and negative VDC over 2. Okay, sama saja. Okay, and then for your line to line voltage, you will get a staircase waveform, with a shape, staircase shape, waveform shape. And there are few level, which is you can see from here, VS is VDC, VDC over 2, negative VDC, and negative VDC over 2. So these are the level for the line to line voltage. And you can find this level of this phase voltage and line to line voltage using all the level that you have calculated in each of the mode from mode 1 to mode 6. Okay. Okay, again, the same things. Okay, this one here, this is mode number 1, mode number 2, mode number 3, mode number 4, 5, and 6. Okay, complete one cycle, yeah. Right, so these are the modes which is yang kita dah lukis tadi. So basically in this slide it's showing you the three modes, but we have a complete analysis from mode 1 to mode 6. If you can refer to the previous slides. Okay, okay, now we go for the equation with regards to the inverter. So in terms of equation for the inverter, it will involve the Fourier series expansion. Okay, where this is the line phase voltage, for three-phase inverter with 120. So if let's say that you're being asked to calculate the amplitude, this one here. So this is the amplitude for the phase voltage, VAN, VBN, or VCN, okay, which is 2 VDC over N pi multiplied by N pi over 3. Okay, this sine N omega T plus pi over 6 is the phase angle. Okay, same goes to here. This is also phase angle. Right. So this is in terms of line to line voltage. You can see VAB, VBC, and VCA. So basically, in terms of the amplitude, more or less the same, except for adding this Z3 over here because of this relationship here. Okay. So that is in terms of the equation that normally being referred when you are dealing with three-phase inverter. Okay, next. Okay, this one here from the original equation just now for the phase voltage and the line to line voltage, we substitute n equals to 1 where we get the fundamental. Fundamental is when n equals to 1, yeah? So you can get the fundamental phase voltage and your line to line voltage, which is your phase voltage when n equals to 1 will be equals to 0 0.3839 multiplied by VDC. For your line to line voltage, it will be 0 0.6753 multiplied by VDC. Okay, so basically from here, this one here, so we solve the pi. Okay. Okay, so 2 divided by pi and sine pi over 3. Okay, and then we just left with the VDC. That's why you can get this value. We can give a try from the equation. This equation, substitute when n equals to 1, and then you solve everything except for VDC. You will get this value over here, these two value for phase voltage and your line-to-line voltage. Right, next. Okay, this statement is actually want to show you the comparison between 180 and 120 operation. Okay, uh, one, two, this is not one, this is two. Sorry for the typo. For 120 degree, there are two switches that we conduct for 120. Okay, so if let's say that you are comparing in terms of switch utilization, penggunaan switch, switch utilization. So you can see that, okay, for 180, it used three switches. These three switches will be turned on at every 60 degree, right? For 120, it used two switches. Okay, which is by right for the switch utilization, the indicating factor is that if let's say that the more you can use all of the more number of switches being used, the better the switch utilization will be. So in this case, 180 has a better switch utilization because there are three switches that being turned on instead of two switches in 120. So that is what we call in terms of switch utilization here. Right. Then that is why 180 conduction is preferred and normally being used for three-phase inverter. Okay, one more thing is with regards to the fundamental component, which is the amplitude. You can see, if let's say that you can recall back from the fundamental component or N and the output, output voltage will be out. Okay. For 180, so the equation that we use to find the amplitude will be this one here, which is 4 VDC over n pi multiplied by sine n pi over 3. So for 120, the equation that we use is 2 VDC over n pi sine n pi over 3. So from here you can see, okay, this is 4, this is 2. Obviously, the equation before is will lead you to a higher fundamental, a higher amplitude, right? So that's why in terms of fundamental, 180 is more preferred because the fundamental value is higher as compared to 120. Okay. So that is in terms of the comparison between the 180 and 120 conduction. In terms of the THT, I'm not too sure which one is better, but I believe, I predict it will be 180. And we haven't checked during our lab session on the THT for both of the conduction. So maybe if let's say that you have time, you can always check what will be the better THT. Is it 180 inverter with 180 or inverter with 120? Okay. Right, so we go for exercise 3. Okay, exercise 3, you have three-phase inverter. Okay, so this three-phase inverter will be the interface between renewable energy source. You can have maybe PV panel for the renewable energy source. You can have a wind turbine. You can have any type of renewable energy sources. And our local load, okay, our local load over here, you can have maybe resistive load or inductive load or any other type of load. Okay, and this inverter, okay, experience unbalanced three-phase load. Okay, unbalanced three-phase load. where RA equals to 20 ohm, RB equals to 50 ohm, and RC equals to 20 ohm. Okay, so we have this unbalanced load over here. Right. So giving the fundamental frequency F naught equals to 50 hertz. Okay, your DC line voltage is 300, VDC equals to 300 volt. And okay, here what the mode of conduction is 180. Okay, what you need to do is that you need to sketch the waveform of getting signal S1 to S6, the phase voltage waveform, and phase current waveform. Okay, so this is basically you need to sketch using graph, the appendix that been given. Okay, and then there is a continuous sentence, which is you need to include the corresponding equivalent circuits with S here for each conduction sequence. So which is equivalent circuit from mode 1 to mode 6, the one that we have discussed before. So you need to include from mode 1 to mode 6. Okay. So first thing, what you need to do is that you need to draw the gating signal waveform so that you'll be able to come up with the switching sequence. So for 120, okay, you use two what we call shaded for two box over here, two section over here. So to indicate that this is 120. Okay, if let's say the 180, you need to shade three box, something up to here. Okay, this is for 180. Okay, once you shaded all these gatings in a waveform and you identify the switch for each of the modes, so you can come up with these modes over here from mode 1 to mode 6. Okay, next, then you'll be able to continue with the analysis using the equivalent circuit to find the level for this phase voltage and also phase current over here. Okay. So we'll start with mode number 1. Okay, for mode number 1, again, we will have S1 and S6. The switching sequence will be the same here. Okay, you need to follow this one over here. Make sure you do. You'll be able to come up with these what we call this arrangement of the switching sequence from mode 1 to mode 6. Okay, mode 1 we have S1 and S6. Okay, first thing you need to find the R equivalent. So you can see RA is connected to the positive terminal of your DC line voltage. Why? Because S1 is the upper switch in phase A. Okay, RB is connected to the negative terminal of the DC line voltage because S6 is the bottom switch for phase B. Okay, so the equivalent resistor will be equals to RA plus with RB. RA from the question is, okay, RA is 20 ohm, RB is 50 ohm. So RA plus with RB, you get 70 ohm. Okay, next you need to find the current. Okay, we are using Ohm's law for the current. VDC link that been given in the question is 300. So 300 you divide by 70, which is the R equivalent that we calculate in step number 1. So you'll get 4.29 ampere. So this is the value for the current. Okay, in step number 3, where you need to find the phase voltage, your VAN, since it's been connected to the positive terminal, the flow of current and voltage, they are the same. Both are heading to the same direction. So VAN will be equals to I multiplied by RA. I from step 2, which is 4.29. Okay, here. Multiplied by RA. RA is the value that been given in the question, 20 ohm. Okay, substitute that. Then your VAN, you will get 85.8%. is percent vote, sorry, 85.8 vote. Okay, VBN. Okay, so look at here, it's connected to the negative terminal, right? And this is the direction of your current is here, your voltage in the other way, in the other direction. So it has, so don't forget to add the negative sign over here to indicate that reverse polarity between your voltage and current. So VBN will be equals to negative I multiplied by RB. Our I we already calculate in step number 2, which is 4.29. You multiply by RB is given in the question is 50 ohm. So you get negative 214.5 volt. This is for VBN. Your VCN will be equals to 0 since there are no switches that being turned on for phase C. Okay, next. In step number 4, if let's say that you've been asked to find line-to-line voltage, yeah, VAB, VBC, and VCA. Okay, you can continue in finding this line-to-line voltage. Okay, and then in terms of phase current, IA, IB, and IC, so this using the equation that I mentioned earlier, IA will be equals to VAN over RA, so you get 4.29 ampere. IB, you get negative 4.29 ampere, and IC, you get 0. Again, maybe I can rewrite the equation. This one here, IA will be equals to VAN divided by RA, IB, VBN divided by RB, and IC is VCN divided by RC. So these are the equation to find the phase current. Okay, so we proceed to mode number 2. So mode number 2, we have S1 and S2. S1 is the upper switch for phase A. S2 is the bottom switch for phase C. So you draw these equivalent circuits here. Okay, so step number 1, R equivalent will be equals to RC, RA plus with RC. Your RA is 20, your RC is also 20, so you get 40 ohm for your R equivalent. Okay, for step number 2, you need to find your current. So the current VDC is 300 divided by the equivalent resistor of 40 ohm, you get 7.5 ampere. Okay, next, step number 3, you need to find your phase voltage. VAN, I multiplied by RA, you get 150 volt. VBN equals to 0. There are no switch that is turned on for phase B. And VCN will be equals to negative VDC, negative 150. Right. So for line-to-line voltage, if let's say that is needed, so these are the calculation. Okay. For and then for the phase current, IA is 7.5 ampere, IB is 0, and IC is negative 7.5. So you have this information of your phase voltage here and your R of the loads. You can always find your current over here. Okay, so for mode C, you have S2 and S3. Okay, so S2 is the bottom switch for phase, is the bottom switch for phase C. S3, the upper switch for phase B. So that you'll get this equivalent circuit. Okay. Okay, step number 1, R equivalent, RB plus with RC. So 50 plus with 20, you get 70 ohm. For the current, it will be equals to 4.29. It's basically VDC over R equivalent. Step number 3 is your phase voltage. VAN equals to 0. There are no switch that we turn on for phase A in mode number 3. VBN equals to 214.5. So here, this one over here, VBN. And our VCN, it will be negative 85.8 volt. Basically, your current is 4.29. You multiply by RC is 20. You get 85.8 volt. So these are the line to line voltage if needed. And then, okay, in the question for phase current, because we need to find the phase current, IA will be equals to 0 ampere. IB is 4.29 ampere and IC is negative 4.29 ampere. So this is for mode number 3. Okay, now we go for mode number 4. Mode number 4, we have S3 and S4. So S3 is the output switch for phase B, S4 is the bottom switch for phase A. So this is the equivalent circuit that's showing you where is the position of RB and RA. Okay, again, the step need to be followed, which is find the equivalent resistor. In this case, it will be equal to 70 ohm. Okay, in step number 2, find the current. Current will be equals 4.29 ampere. Step number 3, find the voltage. And also, you can find line-to-line voltage if needed, and then you punya current lah. Okay, IA, IB, and IC in order to answer for this question. Yeah? So IA will be equals to negative 4.29 amp. Okay, IB as 4.29. IC is 0. Okay, so this is the value for your phase current IA, IB, and IC. So for mode number 5, you have S4 and S5 that being turned on. Okay, S5 is the upper switch for phase C, S4 is the bottom switch for phase A. So this is the equivalent circuit. Again, the same things. You need to find the equivalent resistor RC plus RA. You get 40 ohm. Here, step number 2, you need to find the current. You get 7.5 ampere. Step number 3, you need to find your phase voltage. VAN will be equals to negative 150, VBN 0, and VCN is positive 150 volt. Okay, and then we have our line-to-line voltage, VAB, VBC, and VCA. As for our current, it will be equals to negative 7.5 ampere. IB will be equals to 0, and punya IC will be equals to 7.5 ampere. IA negative 7.5 ampere. IB is 0 amp, IC is 7.5 amp. So this is how you get the value for your phase voltage and phase current. Right. Okay, so you need to do for mode number 6. So for mode number 6, we have S5 and S6. Okay, S5 is the upper switch for phase C. S6 is the bottom switch for phase B. Okay, step number 1, you need to find R equivalent, which is RC plus with RB. Okay, RC kita berapa? RC 20 Okay, RC is 20. RB kita? RB, where is RB? 50. So you get 70 ohm. Okay, this is for R equivalent. So step number 2, you need to find your current. I will be equals to VDC over R equivalent. So it's 300 divided by 70. 300 divided by 70, you get 4.29, Okay, 4.29 ampere. So step number 3, find the phase voltage. VAN will be equals to 0. VBN will, it will be equals to negative I multiplied with RB. So negative 4.29. So multiply with RB. Our RB berapa? 50 So berapa awak dapat here? What do you get for here? For VBN negative?
Negatif 214.
Ah,
0.5.
0.5. Okay. So negative 214.5 volt. So that is for VBN. VCN dapat
85.8.
85.8 volt. Okay, so these are the voltage. Okay, let's say that I just proceed in finding line to line voltage if let's say that is needed. So VAB it will be equals to 214.5. VBC adalah berapa ni? VBC will be negative.
Negative 300.3.
Okay, negative 300.3. Thank you. QVCA, VCN minus VAN, it will be 85.8 volt. So our IA, it will be equals to 0. IB, it will be equals to negative 4.29 M. And your IC will be equals to positive 4.29. So basically you already get all the required parameter, value of your phase voltage and also your phase current. So next step, from here, you can sketch the waveform. So this is here. This is where we sketch the waveform over here. So the sketching for the VAN and our phase voltage here. Okay. So you need to sketch for each of the modes. So this dotted line represent the section for each of the modes. So make sure you sketch accordingly and make sure it is not a very skill sketching. You tak payah you nak kira, you nak measure, okay, this is how many cm or each of the box. No need. Just rough estimation on the level as long as the level are logic. For example, like okay, in mode number 1, VAN is 85.8 volt, right? Okay, mode number 2, VAN is 150. So make sure the level is correct, appropriate, which is it should be 85.8 should be lower than 150. So you don't what we call sketch 85.8 is higher than 150 in the waveform. So because it will give you the impression that the level is different. I mean like the one that 85, it will be you will give an impression that 85 is higher than the one in this mode number 2 here. Although from your calculation, mode number 2 is 150 because the marks is being distributed differently. So make sure for the sketching, at least you'll be able to sketch the correct waveform. All right. Okay. Okay, now we go for exercise 4. Okay, so for this exercise 4, okay, this is one of the past year's examination questions for on the is it three phase on the inverter, but in this exercise actually we combine DC to DC and inverter, as you can see from this figure over here. You have the element of your DC to DC converter, okay, plus with DC to AC. Boleh nampak from this part over here, right? Okay. Okay, I'm going to explain on how to read this table for first. First, figure 4. Okay, the input. So this PV module is your input. Okay, so the output of this PV module, as you can see from here, is VPV. That is the output of the PV module, and this VPV is connected directly to your DC to DC converter, which is your VPV will be equal to your input voltage or source voltage of your DC to DC converter. Okay, so VPV, if let's say that you refer to table 4.1, PV output voltage is 48 volt. So your input voltage of your DC to DC converter is 48 volt. Right. Next, the output of this DC to DC converter, you have V out over here. So you can see here is a direct connection. V out and then the input of your inverter. So V out will be equals to VDC. V out of your DC to DC converter is the input for your inverter DC to AC. Okay, V out. Okay, look at here, this one here. So your V out is given in the table 4.1 is 120, which is it will be the same as the input voltage of your inverter VDC. Right, so that is how you translate the figures and the parameter that been given in this table over here. Okay, this one here, the third line is your output power. You tengok kat sini DC to DC converter, which is this is the output power for DC to DC converter, which is being given 400 watt. Okay, only for DC to DC converter. The switching frequency here, okay, is referring to the DC to DC converter as well. And lastly, the peak to peak ripple output voltage, delta V naught. Obviously, this is used to find capacitor kan in DC to DC converter. Right, so from these two, so you can see your VS is 48 volt of your DC to DC converter. Your V out of your DC to DC converter is 120. So this is what? Step up and so step up, this is actually a boost converter. So if let's say that is not being written what type of DC to DC converter that being used in this particular exercise or question, you'll be able to identify from the value of the voltage that being presented in this question. Yeah? Right. Okay. So that is how basically I just want to explain how you extract the information and how you understand from this figure what are the relationship for each of these parameter. Okay, we are going to focus on the inverter. Okay, this is actually the question. Right, this is continuous from this question. Okay, okay, and this question is mentioned that this three-phase inverter experience unbalanced load. Okay, what you need to do is that you need to provide the expected waveform of the line-to-line voltage in appendix form. So appendix form will be given. So make sure you flip through the booklet of list of formula to find appendix 4 and take it out from the what we call the booklet of list of formula so that you can attach it together with your answer script later on. Okay, appendix 4, you need to attach any appendix number, maybe 4, maybe 3, but as long as it's appendix, that where you need to sketch the waveform, don't forget to include in your answer booklet so that you'll be able to handle it together to the invigilator once your examination is ended. Yeah. Okay. Okay, and then you need to Okay. Okay, sketch the waveform N, sambung. Okay, you need to provide the corresponding equivalent circuit for in each conduction sequence. All right. Okay, so from mode 1, okay, this will represent all the analysis from mode 1 to mode 6. All right. Okay. So the specification of the inverter is given in table 4.2. So this is table 4.2 where we have the fundamental frequency of 50 Hertz, this one here. Okay, these are the load. So your RA will be equals to 5 ohm, RB is 40 ohm, and RC is also 40 ohm. Okay, and then the mode of conduction is given in the question here, which is 120. So if let's say you read the questions for three-phase inverter, then but you didn't find any information on the mode of conduction, whether it's 180 or 120, what you need to do is that you flip through and find the check for the appendix, the one that you need to do the sketching of the waveform, whether it's phase voltage or line to line voltage. Okay, find the so it will be normally it will be in the appendix. So where we have the graph, so this graph you will have the getting signal waveform. So again, if let's say that these you have this one over here, all the waveform here for the switches. Look at the shaded upper area for each of the switch. Okay, if let's say that it being shaded two box which is you can see two line, two dotted line. So these will indicate like it is 120 degree conduction. If it being shaded three box, okay, so three box here, it will be it represent 180. Okay, you can always check in terms of the, if let's say that you look vertically, you can see how many switch are being turned on. If let's say that in each of the mode there are two switches, obviously it's 120. If you find you look vertically and then you see, let's say you have this waveform over here, right? So it indicates 1, 2, 3, three number of switch. So that is 180 conduction. Right. Okay. So okay, now we can start analyze. Okay, using the given parameter of RA, RB, RC, and our mode of conduction is 120. Okay, we can start with mode number 1. Mode number 1 for 120 is S1 and S6. This one over here. It will be the same as the one in exercise number 3. Basically, it's just that this is in terms of the load. The value of load is different. That's all. Right. So for mode number 1, you have S1 and S6. Okay. Step number 1, find the equivalent resistor RA plus RB. So make sure you look at the value that been given in the question. What is RA? What is RB? In this case, RA is 5 ohm and your RB is 40 ohm. So you get 45 ohm here. Okay, then step number 2, you need to find the current. Current will be equals to VDC over R equivalent. VDC is 120, also been given in the question. R equivalent is calculated in step number 1, 25 ohm. So you get 2.667 ampere. Okay, in step number 3, you need to find your phase voltage. VAN will be equals to 13.335. You double confirm with the answer, because this is the one that been given. The answer is being given from by your friend in other group. I don't have the calculator while while assessing this modes of analysis. So I really believe that the answer will be correct from the calculation that been given from from one of the friends in I think in group 3 code, if I'm not mistaken. Right. So always double check. Don't simply what we call believe whatever value that been given here are correct. It might be wrong. I might uh write wrongly. So these are the things. So always double confirm with the values. Okay, and then step number 4, you need to find the line to line voltage. VAB will be equals to 120.015. VBC is negative 106.68 volt, and your VCA will be equals to negative 13.335. Okay, I want all of you to give a try. Make sure you try without looking to this this working step. Try to do by yourself. Once you are confident, then you can. Once you finish that, you can always check with this answer so that you will have some confidence in answering for this question. Right. So for mode number 2, we have S1 and S2. S1 is the upper switch for phase A, S2 is the bottom switch for phase C. Okay, in mode number 2, the equivalent resistor is RA plus RB. You get 45 ohm. The current VDC over R equivalent, you will get 2.667 ampere. Okay, and then your phase voltage VAN is 13.335. VBN is 0 since there are no switch that is turned on for phase B. VCN is negative 106.68 volt. Okay, and then for your line to line voltage, okay, line to line voltage is 13.335. VBC 106.68 volt, and your VCA is negative 120.012 volt. So these are the value of phase voltage and your line to line voltage for mode number 2. Okay, now we proceed. Okay, in mode number 3. Okay, so for mode number 3, we have S2 and S3. S2 is the bottom switch for phase C, S3 is the upper switch for phase B. Okay. Okay, the R equivalent, it will be RB plus with RC. Since the value of RB and RC are the same, which is 40 ohm, so you get 80 ohm for the R equivalent. The current will be equals to 1.5 ampere, 120 divided by 80. VAN will be equals to 0, VBN is 60 volt, and VCN is negative 60 volt. Okay. And for the line to line voltage is VAN minus VBN. So the one in step number 3, VAN 0 minus VBN 60. So 0 minus 60, you get negative 60 volt. VBC, VBN minus VCN. VBN adalah 60 volt minus VCN negative 60 volt. So 60 minus negative 60, negative become plus, you get 120 volt. VCA, VCN minus VAN. VCN is negative 60 minus 0, you get negative 60 volt. Okay. So for mode number 4 is switch is S3 and S4. S3 is the upper switch for phase B, S4 is the bottom switch for phase A. Right. So R equivalent RB plus with RA. RB is 40 ohm, RA adalah 5 ohm. So you get 45 ohm. Okay. The current is VDC over R equivalent. You will get 2.667 ampere for the current. VAN, which is since your RA is connected at the negative terminal, don't forget to include the negative sign over here. So you get negative 13.33 volt. Okay. VBN, you will get 106.68 volt, and VCN 0. There are no switch that been turned on in mode number 4 for phase C. VAB is a VN minus a VVN. You will get negative 120.01 volt. VBC is 106.68 volt, and VCA is 13.33 volt. So again, make sure you do each of these step over here to get more confident in answering for this three-phase inverter question. Alright? Okay. Oh no, kita dah tak ada. Okay, kita so you need to do for mode number 5 and 6, yeah? Okay, mode number 5. Okay. Now you need to give me the answer. Okay, it will be S4 and S5. Okay, S4 is the bottom switch for phase A. S5 is the upper switch for phase C. Sekejap, okay. Okay. Alright, so what is the R equivalent? Okay, RC plus with RB. What is the value? RC plus with RB?
45 ohm.
45, eh? Okay, 45 ohm. Okay, thank you. Okay, the current. Okay, current berapa? VDC over R equivalent. Our VDC is 120 divided by 45. What is the answer?
2.67 ampere.
2 point?
67.
67, eh? Right. Okay. Betul ke kita punya display voltage kita 120? Okay, betul. Right. Okay, next we need to find our phase voltage. Okay, VAN, it will be equals to negative I multiplied by RA. Okay, our current is 2.67 multiplied by RA. RA kita apa? 5, eh? Okay, 5 ohm. So you will get
Negatif 13.35.
13.35. So 13 is negative 13.35 volt. Okay, your VBN equals to 0 and you punya VCN equals to what? 40, eh? Okay. VCN equals to
106.8.
106.8. Okay, so right. So 106.8. Macam tu, eh? Betul, eh? Okay.
Correct.
Alright. Okay, next we need to find our line to line voltage. So VAN minus VBN. Okay, our VN is negative 13.35 minus VBN. So you get 13.35 back, the answer, because your VBN equals to 0. Okay, VBC. VBN minus VCN. Okay, our VBN is 0 minus VCN is so negative 106.8 volt. And your VCN minus VAN. VCN is 106.8 minus negative 13.35. Berapa?
120.15.
Okay, 120.15 volt. So thank you. So these are the value for your phase voltage and line to line voltage in mode number 5. So you're going to do for mode number 6, the last mode. Okay, so for mode number 6, we have S5 and S6. Okay, S5 is the upper switch for phase C, S6 is the bottom switch for phase B. Okay, step number 1, R equivalent, it will be RC plus with RB. Okay, so what is the value? RC is 40, is it? RC 40, RB is it also 40?
Yeah, 80 total.
Okay, 80,
Yes.
right? So 80 ohm for the equivalent resistor. Okay, and then for the current, okay, 120 divided by 80, what do you get?
1.5 ampere.
1.5 ampere. Okay, and then step number 3, VBN, you will get 0. VBN is negative I multiplied by RB. So negative 1.5. RB is 40. What will be the answer?
Negative 60.
Negative 60, right? Negative 60 volt. This will be positive 60 volt. Right. Then the last one, VAB. Okay, VAN minus VBN, you get 60 right here. VBC, negative 60 minus negative 60, negative 120 volt. VCA, 60 minus 0, 60 volt. So these are the value for your line to line voltage and your phase voltage. Yeah? Okay, so done for all 6 mode 1 until mode 6. Okay, so next step, you need to sketch in the appendix for the waveform of your line to line voltage. Only line to line voltage here. Okay, settle on the question number 4. If let's say that do you have any question, open up your mic and ask so that I can explain in any parts that you feel that is not that very clear. Always ask, yeah. Right? Ada soalan? Any question? Kita boleh proceed kepada exercise 5, the last exercise.
Boleh, Prof.
Boleh. Okay. Now we go for exercise 5. Right. So for exercise 5, okay. Apa soalannya? Okay, you have 3-phase inverter. Okay, so this 3-phase inverter, here it's experience phase voltage here. Okay. Set. Mana phase voltage over here. Okay. So this this 3-phase inverter, okay, it has experience and output, which is I think it's shown in figure 2C code. I think this is wrong numbering. Okay, DC link voltage that been given is 200 volt. So VDC equals to 200 volt. And the frequency is 50 hertz. Okay, what else? What you need to do is that you need to, okay, waveform again. That's why I keep on mention that for the 3-phase inverter, it's always that you will play along with the waveform. So you need to predict the expected waveform of line-to-line voltage. Okay, and then you need to do this analysis of equivalent circuit in each conduction sequence. Okay, and then you can sketch the waveform in Appendix 1. So always refer in the list of formula booklet and find Appendix 1. Take out from the booklet and then insert it together in your answer books later. Okay. So this is three-phase inverter circuit. Okay. So this three-phase inverter circuit has been connected to three-phase load. So look at here. Okay, RA that been given is 30 ohm. Okay, and then RB and RC over here. Okay, RB and RC here. So far, you don't have any information because the one that been given is only for RA equals to 30 ohm. So basically, you didn't know any information with regard to RC and RB. You can't simply assume that this is a balanced load because it's not being written in the question whether these load are balanced or this load is unbalanced. So basically, there are two conditions for the load. So the load can be a balanced load or it can be unbalanced load. So since there are no information for RB and RC, you tak boleh assume, you can't simply assume, okay, this is balanced load. RA will be equals to RC will be equals to RB. No. Okay. So just leave it there. Just leave it as unknown first, because later on we can do the analysis to find what will be the value for RB and RC. So this is unknown. RB and RC is both are unknown. We already have the information. We only have the information of RA equals to 30 ohm. Okay, DC link voltage 200 volt, frequency 100 and frequency 50 hertz. Next, okay, this is following this exercise. It gives us this waveform over here. Okay, this is the waveform of phase voltage VAN, VBN, and VCN. Okay, right. So first thing, if let's say that you get this kind of question, okay, first thing what you need to do is that you draw this dotted line over here, okay, so that you'll be able to identify the modes. All right. So each changes of the level, you can see, okay, let's say this one change to this level, change to this level, this to this level, yeah. So each changes of the level, whether it's going up or going down, will indicate the changes in the modes. Okay, so that's why you can draw accordingly this dotted line to differentiate the modes from mode 1 to mode 6. Okay, so you will have 1, 2, 3, 4, 5, 6 mode. Okay, look at here. Before that, the x-axis from 0 to 20 millisecond, which is this 20 millisecond is 360 in degree here. It's 2 pi. Right, 10 second is pi or 180. Right. Okay. What else? Okay. And then now once you already draw this dotted line, okay, next identify what are the information that been given in this figure. Okay, number 1. Okay, it gives us the information of this one over here, which is the level of voltage for VAN in mode number 1. The level of voltage VAN in mode number 1 is 171.40 volt. Okay, so in mode 1, okay, VAN that been given is 171.43 volt. Okay. Okay, if I see that you look vertically, okay, go for mode number VBN. VBN, okay, this is the level of your VBN. It's somewhere between 30 to 40, negative 30 to negative 40 volt, right? So basically you're not sure. Might be 34, it might be 35, negative 34 or negative 35 volt. Since you are not sure, you just make it is unknown. Okay, don't simply agak-agak, you tak boleh estimate. No, jangan estimate. If tak sure, make it unknown. Alright. So your VBN will be unknown. Okay, your VCN, okay, this is obviously lah at 0. So you can put it, VCN will be equals to 0 for mode number 1. Okay, what else? Information that been given from this figure. Okay, look at here. You have this negative 50 here, right? This one over here. At mode number 2, your VCN will be equals to negative 50. Okay, that is information that been given from this figure. Okay, and then you can see here, your VBN equals to 0 because that is obviously the waveform is at 0. Okay, so VBN will be equals to 0. How about VAN? Here, so this part over here. Is it 150? Is it 148? You are not sure, right? So since you are not sure, leave it as unknown. Okay, so VAN is unknown. Okay. Okay, so basically you are the two information. In mode 1, your VAN will be equals to 171.40 volt, and in mode number 2, your VCN equals to negative 50 volt. So these are the two information that been given from this figure, along with VCN here. In mode number 1 equals to 0, and your VBN in mode number 2 is also equals to 0. So mode number 1, VAN that been given is 171.43 kV BN, and your VCN tadi apa? VCN is 0. This is not sure. Okay, just leave it there. Don't worry. Okay, mode number 2, VAN, VBN. Just now. Okay, VAN not sure. 0. Just put it a question mark. VBN is 0. Your punya VCN that been given is negative 50 volt. Okay, so these are the information. Okay, and then from here, you need to identify the mode of conduction, whether this inverter is being using 180 or 120. If let's say that you read from this question, it does not mention any mode of conduction. Okay, so what you need to do is that refer to this appendix 1. In this case, it's appendix 1. If let's say that in your question, maybe appendix 2 ke 3 ke 4, go to that appendix and check the gating signal waveform. Again, the graph paper, like I mentioned earlier, check on the gating signal waveform. If it being shaded to box like this, okay, it will indicate that this is using 120, and you can always check in each of the mode how many switch that being turned on. If let's say that in each mode 2 switches 120, if 3 switches 180. So if let's say that 180, okay, there will be 3 box, like 3 sections that will be shaded there to indicate that this is 180. So always check. Okay. Once you have that information, you are already confirmed, okay, this is 180 or this is 120, you can proceed to do your analysis. Okay. Okay. So I already checked the appendix 1. Okay, the mode of conduction is 120. So we're going to do for 120, yeah. Okay, we'll start with our analysis in mode number 1, whereas S1 and S6 are being turned on. Okay, this one over here. Okay, first you need to, the step will be the same. There are 4 steps you need to follow. Make sure you follow the step. Okay, number 1. Okay, I will explain this. Sekejap Okay, the equivalent resistor R equivalent will be equals to RA plus with RB. RA is being given in the question, which is 30 ohm. Okay, put it there. RB, you don't know yet what will be the answer. Okay, just leave it as RB. Okay, then continue your working step in step number 2, where you need to find your current. So your I will be equals to VDC over R equivalent. Your DC link voltage that been given in the question is 200 volt. You can substitute the value straight away, no problem. R equivalent, you can take it in step number 1, which is 30 plus with RB. Okay, so this part over here is unknown. Sekejap. Okay, this part over here is still unknown. So you haven't know yet on the what will be the value for your RB. Never mind, proceed to the next step, which is you need to find your VAN, VBN, and VCN. Okay, VAN will be equals to I multiplied by RA. Your VN is already been given in the question, which is 171.43. This one over here in the figure just now, right, in the waveform. Okay, will be equals to I is the one here, 200 divided by 30 plus with RB here. Okay, multiplied by RA is already been given in the question, 30. So since you substitute all the value, so the unknown value will be RB, right? So you can solve for your RB. So your RB you will get will be equals to 5 ohm. Okay. Once you already know this RB equals to 5 ohm, you can substitute back this value of RB inside the current equation here in step number 2, so that you'll be able to find your current for this mode number 1. So once you substitute RB with, equals to 5, you will get your current will be equals to 5.714 amp. Right? Okay. Next. Okay, you need to find, remember in mode number 1, VBN is unknown, right? So you need to find what will be the value for your VBN. Your VBN, refer back to this connected to the negative terminal of your DC line voltage. So the RB, I, dah calculate tadi, bila once we know the value of RB, I will be equals to 5.714, substitute back in I here, multiply by RB, that is now in step in finding VAN just now, you will get negative 28.7 volt. VCN is equals to 0 as identified from the figure just now. Okay, so basically you already have the information, the value of your VAN, VBN, and VCN. Substitute to find your line to line voltage, VAB, VBA. So this is how you value of your VC. Okay, for mode number 2, then we proceed. So far, we know the value of RA, 30 ohm, okay. RB is 5 ohm. So far, the unknown is RC. So you need to find what will be the value of your RC. Okay, we'll proceed in mode number 2, which is in mode number 2, you will have S1 and S2. S1 is our switch for phase A, S2 is circuit. The step will be the same. Step RA plus with R plus RC unknown. Okay, yet. Okay, never mind. Proceed with the next step. Your current. Okay, VDC over R equivalent, which is 200 divided by 30 plus with RC. Okay, still unknown because you don't know the value of your RC. Don't worry, you can continue the step. VAN will be equals to this one over here, I multiplied with RA. Okay, since your current here, 200 divided by 30 plus RC multiplied by 30. So far you can't solve for VAN yet because you need to find what will be your value. VAN will equals to 0. We formed just now. VCN negative 50 will be equal to negative I minus. So I is in step number 2 by RC. Obviously you can solve because the only unknown is R. So your RC. So ini adalah saja. Okay, what is next? Apa bawa ke kiri be able to solve for your RC. RC you get 10 ohm. Okay, once you already know the information of your, put this back in your current equation as well as in your VAN equation to find the corresponding value. Right, so your VAB will be equals to 150, BC will be equals to 50 volt, and your will be equals to negative. So now basically you dah tahu lah information. RA is being given in the question 30 ohm. Calculate for mole ohm. In what number? RB and RC. Number 3 611223. So switch 2 and switch 3. So mode number 3, 4 and so on, it will be easy because you already know all the value for your resistor RA, RB and RC. Okay, RB 5, RC 10. Okay, 10. So you get 15 ohm. Current VDC over R equivalent. Okay, your DC link voltage is just now. Is it 200 or is it 300? 200. So 200 you divide by 15. Apa? What do you get for the current?
13.33 ampere.
1.33 ampere. Okay.
Ah,
Okay, 13.33 ampere for your current. So your VN will be equals to 0. There are no switch that been turned on for phase A. VBN is I multiply B with RB. So 13.33 We multiply with RB adalah 5. Okay. So what you get for your VAB? Okay. Okay, VBN. What do you get for your VBN?
six point 65.
66.65, eh? Okay, thank you. Your VCN? Darab dengan 10, eh? RC kita 10. So, kita akan dapat, is it 133.3 ke?
Yes, betul Doktor.
Okay. Okay. So, VAB?
Negative 66.65.
Okay. BBC, BBC berapa? 66.65 minus negative 133.3. BBC.
199.95.
Okay. All right. Okay, so these are the value for your line-to-line voltage in mode number 3. Okay, now we do for mode number 4. Okay, so for mode number 4, we have S3 and S4. Okay, S3 is the upper switch for phase B. S4 is the bottom switch for phase A. Okay, step number 1, you need to find the equivalent resistor. So RA plus with RB, RB plus with RA. RB kita 5, RA kita 30 kan. So you will get 35 ohm. Okay, step number 2, find the current. Current will be equals to VDC over R equivalent. The ceiling voltage kita is 200 divided by 35. Okay, find me the answer for that. VAN will be equals to negative I multiplied by RA. VBN will be equals to positive I multiplied with RB. VCN will be equals to 0. Okay, step number 4. VAB, VAN minus VBN. VBC, VBN minus VCN. And lastly, VCA is VCN minus VAN. Okay, current 200 divided by 35, what do you get?
5.71.
Alright, 5.71 ampere. Okay, VAN negative.
Negative 28.55.
Alright, thank you. Okay, VBN
171.3.
alright. Okay, so 171.3 volt. Okay, VAB berapa VAB?
Saya rasa terbalik kot.
Ha, terbalik. Apa yang terbalik?
Nilai VAN dengan VBN tu. Yang terbalik.
Ah, ha?
Sorry.
Set. Dan maksudnya apa ni? Oh ni ini 171 ke?
Ya.
Oh okay. So BBN tadi berapa tadi? 28 eh? 20 berapa?
28.55.
Alright. Okay. Balik Alright. Okay. So VAB. BAN minus BBN. So awak akan dapat negatif lah. Negatif berapa ni?
199.85.
199.85. Okay, VBC, VBN minus VCN, you will get 28.55, 28.55 volt, and your VCA adalah 171.3. Okay. Alright. So this is for mode 3 and mode 4. So basically I will follow step there, follow the step, and then complete for mode 5 and mode number 6. So once you have completed all the modes, don't forget to sketch the waveform. Okay. Okay, so I will leave it this mode number 5 and mode number 6 for you to fill in the blanks. Okay. Mode number 6 over here. S5, S6. This is S4, S5, 10. Okay, you can fill in the blanks with your answer for mode number 5 and mode number 6. Okay. Right. Sepanjangnya okay. So kita we go for this the last one. We are approaching to the end of the three-phase inverter notes. Okay. So previously we have learned that three-phase we can use two control method, which is 180 and 120 conduction. Okay, there are another one method which is what we call as PWM, similar to single phase inverter, the one with unipolar and bipolar PWM. But the difference is that in terms of the reference signal, where in three-phase inverter we are using three reference signal, tiga reference signal for phase A, B dan juga C, and these three reference signal will be compared with one high frequency carrier signal. Okay, these are the switching rules for S1 until S6, and these are the implementation of the inverter using PWM. We call it as sinusoidal PWM, yeah. So the red one will be the reference signal for phase A, which is the akan affect S1 dan juga S4. Okay, the blue line is the reference signal for phase B. It will affect the on-off for your S3 and S6. Yeah. The green one is VMC. Is the reference signal for phase C. It will affect the on-off switch for S5 dan juga S2. Okay. So macam biasa, every intersection point there will be an output. Yeah. So these are the output waveform. Ini adalah VAN, phase voltage, VBN. VAB is the line-to-line voltage. Yeah? Okay. So you can see it has quite a number of pulses kat sini. Bukan pulse square pulse shape ni, because as you can see from here, there is quite a number of your switching number of high you punya carrier signal, which is it indicates that you are this waveform here is using high switching frequency, maybe around 1 kilohertz perhaps. Okay. All right, and then this one here. Okay, this is from the inverter circuit. This is from the hardware where we observe the waveform in the oscilloscope. You can see this is line-to-line voltage, output voltage, this is the phase voltage and also your phase current. So you can see for your phase voltage here, you can see this kind of a small spike over here. mainly maybe affected to the filter or maybe the load, because this is experimental results, so there are lots of factors that will contribute to the quality of the waveform. Okay, in terms of setting, this is example saja. Okay, so in terms of setting, DC link voltage that we use is 100 volt. The MA, the amplitude modulation index, is 0.8, and the switching frequency is 2 kilohertz. Right. Okay. So, okay, this is, we come up to the end of our slide for three-phase inverter. So basically, for the inverter, we have learned so far. Kejap, let's see kalau saya boleh buka in new. Kejap. Where screen Okay, so for inverter, we have learned so far on the single phase and on the three-phase inverter. So for inverter, okay, basically we have learned on the single phase inverter and three-phase inverter. Okay, so for single phase inverter, there are three control methods that we have learned, which is on the square wave. Okay, bipolar PWM and unipolar PWM, right? So this is for the single phase inverter. Okay, and then see here. Okay, so for single phase inverter, okay, this is using fixed pulses. Okay, the related equation will be this one over here. For VDC over N pi, if let's say that this is full bridge inverter, okay, for VDC over N pi in peak, kalau let's say you want to do in RMS, awak jangan lupa lah letak set 2 dekat bahagian denominator. Okay, and then you have this impedance, okay, the equation for the impedance, okay, and then obviously you punya current. Okay. 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 And then for this PWM, whether it's bipolar ataupun unipolar, okay, in order to find your fundamental component ataupun you punya harmonics voltage, you need to use this equation over here, MA multiplied by VDC. Okay, this MA adalah dalam peak value ya. Alright, in term of impedance sama saja, menggunakan equation yang sama. Okay, and then same goes with your current. Okay. Apa lagi? Oh, okay. And then in term of the power, okay. So both inverter using square wave ataupun PWM, okay, it will use the same equation for the output power, which is if let's say that your current is in peak value, you need to change to the RMS, or if let's say that your current is already in RMS, it's just I squared multiplied by R. This equation valid for both R load and RL load. Yang the one ada impedance lah. Basically, the one with impedance, you just substitute lah. They just multiply with R only. No need to consider the effect of the inductor. Okay, and then what else? Oh, okay. So the total power absorbed by the load will be equals to summation of all power that you have calculated and considered using the harmonics order. Okay, how many harmonics order that you want to do? It depends. You need to refer to the question. The question will state that whether you need to do your calculation maybe up to n equals to 7, maybe up n equals to 11, 13. It will be written in the question. Yeah? Right, and then in terms of the THT, both are using voltage ataupun current sama saja. You cuma tukar punya variable saja. Both are using the same equation, whether it's inverter power up by square wave ataupun inverter that been power up by PWM, unipolar or bipolar. Okay, so these are the value for, the equation for the THT, whether it's voltage or current. So basically for single phase inverter, the question will more or less will uh, will go around this. Basically, you need to find the THT, you need to find the output power. Okay, and then one more thing with regards to PWM, kita ada lagi satu equation which is MF. Okay, MF will be equals to your switching frequency divided by your output frequency. Okay, you need to have the information of your MF. Why is that? Because so you need to know your MF so that you be able to use the value in normalized Fourier coefficient table. Normalized Fourier coefficient table, whether it's bipolar ataupun unipolar table. Okay. So if let's say that you have bipolar, you need to make sure that you refer to the correct normalized Fourier coefficient for bipolar PWM. Is for unipolar, refer to the correct table. Yeah. Okay. What else? For the single phase. Yeah, I think that is basically on the single phase. So basically the question will be linger around this. You need to find the THT, the power, and you need to use the information from the normalized Fourier coefficient table for bipolar and unipolar. So these are the things that you need to make sure that you are familiar and you'll be able to solve using the equation here. And you can always refer to the example that have been given in the lecture notes. So basically we cover all of this. Okay, and then as for three-phase inverter. Okay, untuk three-phase inverter. So for three-phase inverter, you have either 180 conduction ataupun 120 conduction. Okay. Right. So make sure you be able, number satu, understand the gating signal waveform so that you be able to see the switching sequence. Ni untuk kedua-dua 180 dan 120, so that you be able to see the switching sequence. Switching sequence for each mode. Mode 1 to mode 6. Okay, once you identify the switching sequence, then you'll be able to do the analysis. Okay, to find the phase voltage and your line-to-line voltage. Okay, using equivalent circuits. Okay, once you yang ini you buat untuk semua mode mode 1 sampai mode 6. So once you get all the level, okay, you can sketch the waveform whether it's phase voltage only or line voltage only, it depends. Okay, so for 120 normally we go for balance load. So far, I haven't asked any soalan, any question on the unbalanced load for 180. But for 120, you can have two conditions, whether it's unbalanced or whether it's balanced or unbalanced load. So which is the excess that we already discussed throughout on the three-phase topic here. Okay. Okay, and then apa lagi on the three-phase, macam biasalah example 2 ada a bit of equation a little bit that you can refer to equation in Fourier. Okay, this is just a simple equation. You can the equation will be provided in the list of formula, so you can just extract from there and then substitute into the value that been given lah. Right. So itu saja. This is screen which is this one over here. I will appreciate that you be able to salin ke, tangkap gambar ke apa-apa yang patut, sebab ini bukan daripada slide, ni saya add on screen. Saya takut bila saya save nanti dia akan hilang. Okay. Okay, so itu saja. That is all for inverter topic on the single phase and three phase inverter. So basically saya dah cover semua on the inverter punya part. Okay, again make sure you write it down, this slide over here, kalau lah you perlukan nak tengok this slide. Ataupun sama saja basically yang sama je yang macam sebelum ni, cumanya saya simplify saja. Okay. Alright. Keep slide updated. What was that?
Doctor,
Yes.
do we have a question in BWM for three phase?
No. Only using 180 and 120 conduction.
Okay, thank you, Doctor.
Okay. Any more question? Okay. All right. Okay. Okay, I think that is all from me. Any more question that you would like to ask me before we end our session for today, our last session for today? Ada